Okay, we're not going to do all of that worksheet, but I am going to do enough to give you an idea of what a slope field is. So, way back when, we talked about taking the derivative of a function of what it represented. It represents three things. What are they? Slope of the tangent line, instantaneous velocity, and you combine two and your rate of change bit. So if I take a function and I take the derivative of it, we looked at getting functions that were slopes, and that confused some of you until you got used to it. So for instance, if we take the derivative of x squared, we get 2x. And that means that at certain points in the graph, you would have a slope, and that slope would differ depending on where you are on the graph. Yes? Beautiful. A slope field is a mathematical or a pictorial way to represent what those slope fields look like. So you'll notice at number 1 at the top, I've given you the derivative of a function. We're smart enough that we can work backwards and figure out what the function is. We'll worry about that later. What I want to do is I want to graph all the possible slopes at all the possible points for that particular function. And instead of drawing these big honking lines all over the place, we just use little dashes. Okay, so in some respects this is a little tedious, but you'll see it's kind of cool when all the pieces fit together. Okay, so for instance in number 1, what function has that derivative? Negative 3x, correct. That wasn't meant to be so challenging, but hopefully things will get better. Okay, so what I'm going to do is I'm going to start plugging in values, and the values that it spits out are going to be the slope values. And then I'm going to fill in the graph with all those little slopes all over the place. And there's a lot more dots than you'll ever have to fill in, but you'll start to recognize the pattern. So this one is going to be ridiculously simple, and then it'll get a little bit more complicated as we move through the other problems. You also want to do a little bit of detective work to make your life a little bit easier. So let's start on the x-axis. Suppose y equals 0. What's the value of the derivative?
0.
Nope. If y equals 0, what's the value of the derivative? Doesn't matter what I put in for y. Doesn't matter what I put in for x. What's the slope of the derivative always? Negative 3. Okay. So at each of these points, I'm going to put a little dash that has a slope of negative 3, and this is not rocket science. We're going to kind of ballpark it here, and we get something that looks like this. And again, as I mentioned, it's a little tedious, and that one's kind of silly. But why is it silly? Because the function negative 3x always has a slope of negative 3. That's going to change in problem number 2. Now we could go and calculate, in fact it wouldn't be difficult, we could calculate what function generates that derivative, but again, that's not what I care, watch out for that. That's not what I care about right now. What I care about is what the slope field looks like. And this one is where we're going to start looking at a little bit of different calculations here. Okay, so let's start with x being 0. If x is 0, which is the y-axis, what's the value of the derivative? 2. Any problems there? Just plug and chug. This one is kind of interesting because everything's going to be vertical. So on the y-axis where x is equal to 0, since there's no y to plug in, we're going to get a value of 2. So you got to kind of ballpark it for a little dash that's got a slope looking something like 2. Let's go to the right. If x is 1, what's the value of the derivative? 1. Okay, which is also known as a 45-degree. Whoops, missed a little bit there. Okay, does it have to be perfect? No, but I should see a change in slope as I move to the right. What if x is 2? 0, also known as a horizontal line. What about when x is 3? Say again? Negative 1. And we'll do one more. What about when x is 4? Negative 2. Without talking specifics, that derivative is a first degree equation. If I take the integral of a first degree equation, what do I end up with? Second degree equation, also known as a parabola. And that parabola will open up downward because you have a negative number, or a negative coefficient, I should say. So again, we could calculate it. The function would be, what is it, negative 1/2 x squared plus 2x? But we don't care about that. We just want to be able to generate this slope field. As I move to the left or the right then, the dashes just get steeper because that's what would happen as you move away from the vertex of that parabola. Question, Chip?
Does the value of C, like you were saying, like the antiderivative, would the value of C impact that slope field at all?
The value of C is what generates all those different shapes. So we would slide it up and down and get those different shapes. So this slope field gives you a picture of the family of possible values. It may also say to you, okay, fine, draw the slope field, but then draw the graph or approximate the graph of the function through the point, oh, I don't know, let's say 4, -3. Okay. So now I have to actually draw the curve of what it looks like. It doesn't have to be perfect, but I do know I'm going to go through this point, and it should kind of follow the general curve of the slope field. So maybe something like that. Okay? And you could pick any point on the graph to generate that curve. Am I too loud? You want to close the door? Are you cheating? Why not? Nobody's watching except the cameras up above your head. Okay, make sense? All right, let's do something a little bit more interesting. I think that's actually number 5 for you, right? Turn the back over. Yeah? Okay. Because I'd like to do one with both an x and a y there, because now we have to plug in more numbers and the pattern's a little bit more difficult to recognize. Do you have any idea what function would generate negative x over y as the derivative? Good, because I would be worried about you if you did. So let's do the slope field and see if we can figure out what that graph would look like. Okay. And we'll use a little bit of logic here. Let's start at 0, 0. What happens at 0, 0? Doesn't exist. Why? 0 in the denominator. So in fact, anytime that y equals 0, there'll be no values. That eliminates the entire x-axis. We can't have any dashes on the x-axis. So let's do the y-axis. What happens when x is 0? Yeah, these would be 0. Now, you could argue that on the y-axis, on the x-axis, you could put in vertical dashes, because those have a slope of undefined, but that's not the AP standard. They want you to just not put any dashes in there. Okay, let's try something like 1, 1. What happens at 1, 1? What's the slope? Negative 1. And having given you that point, where would you like to go to next? 2, 2. Like ballet. What would the slope at 2, 2 be? Negative 1. And? 3, 3. And? 4, 4. And 5, 5. And?
6, 6.
We could go to 6, 6, yeah, but I ran out of space. Go there. Okay, now where do we go?
Negative 1.
Negative 1, 1. What would the slope be at negative 1, 1? 1. Whoa, swing and a miss. All right. Okay. What about 2, 1? Say again? Negative 2. So this has got to be like negative 1, but only steeper. How about 2, negative 1? Like positive 1, but only steeper. And steeper, and steeper. And if I continue building that, what shape do you think we'd get? It's a circle, correct. We'll do the math later as to calculate how we know it's a circle other than the slope field. But you'll see as I continue plugging in numbers, these are going to continue to get more vertical. This is going to continue to get more vertical. And we start to see a pattern here. This will start to level out a little bit more. This levels out. And you start to get this representation of a circle. Okay, and you get the idea. Okay, what about an exponential? Any points that are verboten, that's German for forbidden. Anything that doesn't work there. All right, what if x is 0? 1. X is 0. These are all 1. And notice there's no y to plug in, so we'll be working with these vertical graphs again. What if x is 1? 2. Gets a little steeper. And so what's going to happen as I go to the right? It's going to continue to get steeper and steeper and approach a vertical. What happens when I go to the left? What if x is -1? What's the value of the derivative? 1/2. So it starts to get shallower. And again, notice it's not rocket science here. I have enough there, however, that I should be able to draw the graph through one of these points. Let's do this point. That's 2, no it isn't, that's 1, 2. So if I'm going to go through that point, they're going to kind of go like this. It's going to maybe something like that. General solution versus specific solution. General solution is all the dashes, which gives you that big old picture. Specific solution gives you the actual graph of the function at those points. Make sense? Okay. And like I said, later on we're going to do the math. We're going to do something called separable differential equations, which we'll be able to do the math and calculate exactly what function gives us each of those values with a c term involved. Okie doke. Beautiful. I'll pass out your homework, which is a worksheet. While I'm doing that, clear off your desk, get your dividers, get set up so we can do this quiz so some of you can stop freaking out.